Yeah, hello, welcome everyone. This is the GCPR Excellence Award session. And my name is Reinhard Koch, and I'm currently the president of the DAGM, the German Association for Pattern Recognition. And one of the goals of the DAGM is to promote and support young researchers and rising stars on all levels of their career. The Young Researchers Forum, for example, supports students in our field. So we have excellent bachelor students that have already shown and proven themselves, so they can apply for a travel grant. This year, of course, there is no travel grant, but it's for free. And in addition, we honor best masters. So that is the what we call the Young Researchers Forum Award here. Best Master Thesis Award will be given, and we come to the award itself in a minute. So while this is sponsored by DAGM directly, the other two awards are sponsored by companies. So on the next level, the MV Tech company is sponsoring the best dissertation of the previous year in our field. And this is now already for the 5th year. And we are very glad that the award of €2,500 comes from MV Tech. Okay, and the most prestigious award is the German Pattern Recognition Award. And that is sponsored by Daimler, has been sponsored over the last 10 years with €5,000 yearly. And this award goes to excellent researchers under the age of 35 who have already made an impact internationally. Actually, this award goes back for much longer, for about 30 years, and it was formerly, the first 20 years, it was known as the Olympus Award. And you can go to our DAGM website to view all the awardees, and you might recognize very many of our now colleagues at a very young age, looking funny maybe. So the award is a very good indicator of becoming a professor or a good researcher. And the award itself has to be selected, and it's selected by the DAGM Technical Committee. The Technical Committee is selected by the DAGM General Assembly every 3 years. Please have a look at our website for this. So now, most important is we come to the real awards. So each award is presented by a laudator, and for the first award, which is the Best Master Thesis Award, I call upon Bernd Schiele. And you know Bernd Schiele, he is the director of the Max Planck Institute for Informatics, and he's also here in his position as vice president of the DAGM. Bernd, please.
Yeah, thanks very much, Reinhard. So yeah, it's a great pleasure to present the Young Researchers Forums Award, the Master Thesis Award, as Reinhard said. Just to remind ourselves, right, that this is really in particular to honor exceptional scientific achievements during the master thesis phase. Really, the master thesis is what you are essentially submitting here. And the format actually is that the master thesis is submitted as a paper to the regular conference track with sort of an additional tick, right, that it actually is part of the Young Research Forum. And actually this year, it's great. We have actually 5 master thesis papers that are accepted at the conference. And already this is a great achievement that for all these master thesis people that actually are obviously with their co-authors, get this paper accepted to our conference. That's great. So it's great to see that there's so many young people having great results during your master's thesis. So the committee, as Reinhard said already, is then the DAGM Technical Committee. And this year, because there was actually also some master thesis from my group, I was not part of the committee, so I was excluded here. But now I would like to present the one. So Reinhard, go on. So this year is presented to Yifei Zhang. It's the topic of the master thesis was synthesizing human pose from captions. So it's also a paper, obviously, as I said. The master thesis was done at Aachen, RWTH, and it will be presented later today in the talk session at 4:15. So right, and if we move to the next, next slide, we can. Normally we would now applaud and would be very happy to present the award to the hopefully slightly more exciting looking person here on the right, which is Yifei Zhang. again, congratulations to your award, and we're looking forward to your talk later today. Thank you.
Yes, from my side also, congratulations to you. Yeah. Okay.
Thank you.
And of course, as you know, this also comes not only with this certificate, but with a nice 500 euros to spend on what you want. Okay.
And don't share it with any of your co-authors.
No. So thank you very much again. And we come to the next award. The next award is the MV-Tech Dissertation Award. It will be handed over by Carsten Steger. And Carsten Steger is one of the directors of MV-Tech, but he's also honorary professor at TU München, and he is speaker of the DAGM Technical Committee. And in this position, he is giving in this award. We owe to Carsten that this award can be given because he is the one who brought in the money. And now, Carsten, please, you can give the laudatio.
Thank you, Reinhard. And this is my honor to present this award to Dr. Wladislaw Goljanik for the best dissertation of the year 2019. The DAGM MV-Tech Dissertation Award is awarded to Wladislaw Goljanik. Dr. Wladislaw Goljanik received his diploma in computer science in 2010 from the Moscow Aviation Institute at the National Research University in Moscow, and his master in science in computer science in 2013 from Ulm University. He then worked as a researcher at the German Research Center for Artificial Intelligence, DFKI, in Kaiserslautern, in the Augmented Vision Department from 2013 until 2018, under the supervision of Professor Didier Stricker, and received his PhD degree from the Technical University of Kaiserslautern in 2019. He currently is a researcher at the Max Planck Institute for Informatics in Saarbrücken in the Graphics, Vision and Video group. In his thesis entitled Robust Methods for Dense Monocular Non-Rigid 3D Reconstruction and Alignment of Point Clouds, Wladislaw Goljanik has presented numerous contributions to the fields of monocular 3D reconstruction of non-rigid scenes and point set registration. The proposed methods are original, mathematically sound, and always have been evaluated very carefully. In addition to the theoretical contributions, Dr. Goljanik has proposed algorithms for efficient implementations of the methods, which have been tested in the context of real applications. The thesis is very well written, clearly structured, and represents an excellent reference work for researchers working in the field. So, like Bernd already mentioned, normally we would now applaud. So congratulations on your awards. We are happy that you submitted your thesis this year for the awards, and we are very happy to present you with this award of 2,500 euros.
Yes,
thank you very much.
Congratulations from my side as well. Yeah. Okay.
Thank you very much. Thank you.
You're welcome. Okay, so normally we would make photos, but we have to do now with online. That's how it is these days. Now we come to the most prestigious award. The German Pattern Recognition Award will be handed over by Uwe Franke. Uwe Franke is head of the Image Understanding Group at Daimler Vehicle Automation Systems. But moreover, Uwe is really the initiator who has convinced Daimler to sponsor the award over the last 10 years. And he has been supporting the DAGM and GCPR for a very long time. For example, as a member of the technical committee, and since 2015, he's already also a honorary member of the DAGM. And actually, today might be one of the last official appearances of Uwe as Daimler employee, since he told me that he will officially retire tomorrow. So one of his last actions here, but I'm certain that we will see Uwe again at future conferences. Uwe, please.
Yeah, thank you, Reinhard. Thank you very much, and certainly you will see me again. It's a great pleasure for me to announce the awardee of this year's German Pattern Recognition Award. He got his PhD in 2013 from University of Erlangen-Nuremberg. He was till 2017 visiting assistant professor at Stanford University. And since 2017, He is professor for computer science and visual computing in Munich and co-founder and director of a very new, brand new startup, Synthesia, which aims at digital image synthesis. Most of you will now know who is our awardee. It's Matthias Nießner, and he gets the award for his pioneering research on tracking, reconstructing and visualizing photorealistic 3D face models from video with machine learning and AI. Matthias' research interest lies in the intersection of computer vision, graphics, and machine learning. And despite the fact he's just 33 years old, he has published over 80 publications, including 22 papers at SIGGRAPH journal and 26 papers at our leading vision conferences like CVPR, ECCV, and ICCV. I would like to read the official laudatio. Professor Nießner's face-to-face research in 2016 kicked off the conversation worldwide, followed by his deep video portraits in 2018, neural rendering 2019, face forensics ++ the same year, and neural voice puppetry just this year. This line of work has led groundbreaking progress in a vital area of current interest, the creation and detection of synthesized face videos. It was even recognized by Chancellor Angela Merkel in her cabinet, whom Professor Nießner was invited to advise regarding artificial intelligence-driven video synthesis and ethical consequences. Matthias, congratulations to your great work and to this prestigious award.
Yeah, it should be a big applause.
Yeah, thank you so much.
Where are you? There are you.
Yeah, thank you so much. It's a real honor to receive the award. Of course, it would have been very nice to be there in person and celebrate with all of you. I should also say thanks to all of my colleagues, especially Justus Thies, who was well, specifically instrumental for a lot of these researchers. He did most of the work actually. Yeah, so thanks a lot. I think it's really fantastic that this eventually led to so much impact, but there was of course a lot of luck in it. And yeah, I mean, hopefully next year we will have a physical conference again.
Okay. Yes, thank you very much. And of course, this is not the end. Before I hand over to Matthias, we have, of course, the award lecture now here. Again, Uwe said already your CV, and I was really impressed, of course. You not only have all these academic achievements directly, but also you received an ERC starting grant, the Eurographics Young Researchers Award in 2019. And I looked up at, in 2020 alone, you and your team published 17 papers at the major top conferences. This is hard to top, okay? So now we are really looking forward to your award lecture. From 3D scanning to neural rendering, and I stop my slides here and hand over to you.
Yeah, thanks a lot. Let me see if I can share my screen. Okay. Can you see it?
Yes, of course. Sorry, I was sorry.
Okay. Yeah. So thanks a lot. Yeah, as I said, it's a real honor receiving the award. So for the award lecture, I decided actually to give a fairly general talk, also with a lot of research that actually led to these developments. And I called it From 3D Scanning to Neural Rendering, to give kind of a broad scope of, well, I guess not only my and our research, but also general development in this area. I mean, a lot of the research actually that is happening in my group, but also generally in computer vision as well as computer graphics is, we have a lot of data from videos right now, and we want to use these devices like smartphones to capture the real world in one way or another one. And we're pretty good at capturing videos, but the real thing what we're missing right now is like having like free viewpoint synthesis, like everything we can do in a game, kind of relive the real world in a digital environment in the very same immersive way. And Well, novel viewpoints, and this is just one thing, but also video editing, content editing, and so on. These are many, many things that belong to this. But on a high level, we want to take all the content we see in the real world, and we want to see it kind of virtually. And of course, a lot of these things are inspired by science fiction, Star Trek or so. The holodeck was, of course, one of the big inspirations to me when we started a lot of this work, that we wanted to replicate this. And one side is, of course, the content that we need, and the other side is the displays. We're not quite there yet today. Well, we have reality, we have virtual reality that is, kind of the analog to this, what we can do in terms of displays. And here we can see already that we have kind of immersive environments, but at the same time, it's not quite ready yet. But we see already there's a lot of cool new research that can potentially follow up on this. But as I said, we're not working on the display side here. We are mostly working on the content side. So the question is, how can we capture these 3D environments? And this work in computer vision, actually, or in computer graphics, we started roughly like 2013, when I was back in Erlangen with a lot of discussions with Michael Zollhofer. The Kinect was just available, and we thought, maybe we can do 3D reconstruction, and we can create this kind of content that we need for virtual reality, for augmented reality, and so on. So we wanted to create all the content in kind of an automated way. And the Kinect was kind of a very cheap device. It was like $100 basically. We had a real-time RGBD sensor, and we were like super excited when we got it the first time. And one of the first works we did at this was voxel hashing. And the idea here is we're taking a real-time stream of the Kinect, and we wanted to get a 3D reconstruction in real time, but it's also scalable. The idea was that we wanted to have a data structure which was based on hashes that could actually go beyond a single object, but could go to large environments. And this is very interesting today because a lot of people, of course, use machine learning, but a lot of the data they're actually using on 3D learning comes actually from these methods here right now, specifically from voxel hashing. And I'll later talk a little bit more how this data is actually being used then. But at the time, we were like pretty happy. And at the time, it's like 7 years ago. It's not so long ago. But we were very excited that we got actually pretty reasonable reconstruction. So we got 3D models you carefully scanned that looked something like this here. This was a room scene, right? We had, if you look at the table in the middle here, we're getting a book. We see, the plants on the side are reasonably well reconstructed. So we get quite some fidelity here. And as I said, also the core contribution of this method was that we could do it for large scenes. So we could do it here. This was an outdoor scene, I think in Cambridge, where you could actually pretty much scan infinitesimally large scenes from a scene representation. So the focus of this work was how can we store and how can we efficiently process this data in real time. But at the time, when we're talking about SLAM systems, most SLAM systems had the standard problems that doing things like loop closure was actually not quite possible. So this is a top-down view from a 3D reconstruction from my office at Stanford. And you see, like, if you're going around one loop here, you see that on the top here, unfortunately, the reconstruction doesn't quite match. And this is all the computer vision people will immediately know, well, we don't quite get the tracking right because we don't have global alignment in this method. So this was one of the next things we thought about. Well, we wanted to get a real-time reconstruction with RGBD data, and let us actually fix these problems. And this was what we did in the next work, which we called bundle fusion. So we thought, oh, we kind of do like bundle adjustment in real time, and we wanted to fix the poses as well as the reconstruction in real time. So we wanted to get this globally consistent map of the environment with interactive feedback. And one of the interesting things of bundle fusion here was we basically had a set of sparse features. This was just one of the energy terms. I'm not going to go into much more detail here. But the idea of bundle fusion is you finding a set of, at the time, it was SIF correspondences. I guess today we use some deep learning methods. But basically you're having correspondences, and then you have this nonlinear least squares problem that you're trying to solve, which is actually quite expensive to compute, right? So you have this, for every correspondence in every frame, you're matching against every other frame. And then you have this global set of correspondences that you're trying to minimize this feature error here. And for all of you today who are using a lot of deep learning, this was pretty interesting because we wanted to get this done in real time. So we had to implement our own solver on the GPU. We had custom CUDA kernels, like for every matrix multiply in our Gauss-Newton solver. It was kind of exciting to, really like work on this very close to the hardware and implement everything in CUDA kernels and every little performance piece that mattered here. Yeah, and the result looked something like this. So here we see an example of a video. This was me still at Stanford. I'm holding a structure sensor here. So it's an iPad. In the front, we have the structure sensor. That's basically a Kinect that was manufactured by Occipital. They make these small sensors. You can attach them to the iPad. They sync the camera of the iPad with the depth sensor. And yeah, the nice thing is now you could stream. It didn't quite run on the iPad, but we could stream the data here from the iPad in real time to the computer, and in real time we could get the reconstruction. So it looked it looked something like this here. So it started recording, right? So it's now initializing the connection, and now you see the live reconstruction here in the background, right? And here on the bottom right, you see the reconstruction, how it's being updated when you're getting new data. So I'm basically going around 360 in this room here. And now you see that when the loop is being closed in this room, that the global optimization kicks in. It's actually run all the time in the background. But here, you can see that, it found correspondences, it found matches, and then it fixes the reconstruction, all in real time. It was kind of nice. This was kind of the first system that could do this online. It could do it for relatively large scenes. It had, as you can see here, it can do relocalization. That was quite a robust system, and it's actually still pretty widely used today. So the code is, of course, online, and it's being used for a lot of data sets. Actually, I will get to later. So yeah. And then we can extract the mesh, and here in MeshLab we can look at the reconstructions. So if you're looking at some of the results, it looks something like this. This is the top-down view here of a copy room. And if you're looking closely, you see actually that the fidelity here is actually quite nice, right? Because we have this interactive feedback. We kind of see where we have to scan. We could select where we're going in terms of the next camera positions, and you're getting pretty high quality reconstruction actually this way. So we were quite happy, and for like static reconstruction, it was really interesting. At the same time, we also thought of, can we work on dynamics? But one of the big things we wanted to look at now is take these reconstructions and do semantic scene understanding. So we had specifically like robotic scenarios we had in mind. We had AR, VR scenarios in mind, and we wanted to figure out the semantic understanding of these scenes, ideally actually in real time. And at the same time, there was, of course, like since like 2013, 2012, with like AlexNet and with all the progress in deep learning, we thought maybe we can also use 3D neural networks in order to do semantic scene understanding directly on the 3D scans. And I've given a couple of talks already in the past why I think doing this, like doing learning on 3D, is pretty successful. And one of the reasons is you don't have to learn viewpoint invariance. So we will see that the 3D neural networks are actually pretty efficient. And this was one of our first papers with a couple of colleagues from Stanford. This was Charles Chi was the main author here. He later did PointNet and so on. So we started working on this together in terms of can you come up with good 3D architectures that were good at classifying single objects first, right? And so we did this for single objects, and then we thought, well, maybe we can do this also on larger scenes. And the problem we had at the time, we looked at a bunch of data sets, and we all realized that these data sets are relatively small. So NYU was a big data, I guess it's still a big data set that is being widely used actually for RGBD methods, but it only has about 1,500 annotated frames. And if you're looking through these numbers here, we had the TUM RGBD data set that didn't have labels. They only had SLAM annotations basically. Some 3D, only like 8 scans annotated. Some RGBD was a bit bigger, that has 10K frames. But all of these scenes basically were way too small in order to do some reasonable learning on it. And we thought, well, maybe we can do a new data set, and maybe we can build it directly based on bundle fusion and voxel hashing, the methods we have previously developed that actually gave us pretty good 3D reconstruction, and we could go ahead and annotate them. And this is something we have done in the scan network. So this was still when I was at Stanford. So Reinhard was leading the project too. We had a bunch of undergraduates basically, and also ourselves, and we went around and we started we started scanning a lot of environments. So we had iPads with structure sensors, right? We literally went from home to home. We went to the dorms. We went to university. Whenever we gave a talk, I asked people, hey, could we also scan your offices? And we captured a lot of data like this. And this is eventually what became ScanNet. And the idea was we wanted to take these reconstructions and annotate them in the way that you can see here. So we wanted to annotate semantics as well as semantic instances, right? So we wanted to know object labels and class labels. And in total, we captured about 1,500 scans. So we had 1,500 recordings, and each recording had a few thousand frames. So it was like pretty much reconstructing a room-sized scene, which we could capture with the iPads and the occipital sensors. And in total, we have about 2.5 million frames that we have captured, RGBD. And yeah, this was basically an order of magnitude bigger than everything that was around there. And we spent a significant effort in annotating these scans. So we had a cool annotation interface that Angel Chang did at the time, and she was working with us. She was mainly doing the interface. And the idea there was we could everything runs in a browser for the annotation, and you can Turk it out basically. And then we had a bunch of Turkists helping us, and we got decent annotations, but we realized we had to still fix them later, and we spent actually a lot of manual effort. Mostly Angela spent a lot of effort in annotating or fixing up a lot of things that Turkists didn't quite get right. But yeah, so with ScanNet, we basically have these two main tasks of semantic segmentation and instance segmentation in 3D. And yeah, I would say this was one of the papers that really enabled a lot of future research, including, of course, our own research on top of it. So you could have various combinations now of take 3D geometry, take 2D images, take depth images, and process these with neural networks, and then make instance segmentation methods and so happen. And it's actually pretty exciting. So we have a few thousand downloads now of ScanNet, but we also what's probably even more interesting is we have a benchmark with the hidden test set, and this benchmark actually only went live like 2 years ago, and I think we have now like close to 500 submissions or so on the benchmark. And it's pretty cool, like how the community developed here. So if you're seeing here, this is the instance segmentation benchmark on ScanNet. So if you're seeing here, this column here is interesting. This is mean average precision with 50%. So it's averaged over all classes. And we see, this was like 2 years ago, the best methods were about at 0.24, 0.25, and now we're already at 0.6. So this, like, the progress was being made here was actually quite impressive. And of course, we also developed a lot of methods in our group or in collaboration. So one of the most recent one we had was this 3D MPA. It had already 0.6. This was led by Francis Engelmann in a collaboration with Google and the University of Aachen. And yeah, this was kind of cool that you can see this like progress, how it developed. And I would argue even today, this is not saturated yet. We're only at 0.67, right? So there's still a lot of room for improvement. And of course, there's a lot of teams working on making these kind of things still better. So this was one of the efforts that we thought, well, we had these reconstructions now, and we could actually do, well, reasonable understanding now. So we thought, for like semantic scene analysis and so on, this was kind of nice. So understanding was great, but I wanted to get back to my original point in terms of, but what about the looks? Like, can we use these reconstructions for, kind of creating holograms, creating 3D content that we could put into games or movies, for instance? And most of the time, when you're looking at some of the papers, and this is a screenshot from Bundle Fusion that we did, you see a nicely polished view. But even here, you can already see, right, you're missing a bunch of pieces of the geometry here. But of course, when you're seeing this in papers, people deliberately pick the few stuff that it looks pretty nice. But of course, it is very, very difficult, even if you have a real-time system, to scan every single thing in a scene, right? So when you're now changing the viewpoint in the scene, for instance, here we see from the bottom, we see some views where we actually missing a lot of the geometry here, right? So compared to the 3D models in a video game, this is actually quite poor actually at this point, right? It's not at the level. And here I can say this is our own paper, but a lot of other papers have this too, right? It's fundamentally very difficult to get complete reconstruction. So we have to think about how to possibly get the reconstructions better. And well, as I said, scanning everything and getting everything scanned at the same time is pretty difficult because you sometimes have physical limitations, right? A Kinect has a certain minimum range. You can't go beyond that range. So we thought, well, maybe we can use neural networks here, not just for discriminative tasks, but we can use them for generative tasks. In this case, we were looking at the scan complete work. We have here a partial scan here as input from a large 3D environment. And we thought, oh, maybe we can train a generative neural network in order to predict all these things here on the right. And you can see, this is pretty partial of this room. And then the neural network does actually a pretty decent job in filling in these pieces. So, we spent some time in developing a 3D neural network. In this case, it was an autoregressive network that could actually, do this kind of conditional generative task. We have a partial scan as input, and we want to have the best possible explanation in the respective output. Yeah, and if you're looking at some of the results, it looks something like this, right? This is the partial scan we have here as input, and here we see the respective scan completion. So you see it looks already quite better. Still a bit blobby, but it looks pretty good. We also get the semantics. We can make the network predict those as a proxy task. And we can actually run it in a fully convolutional fashion on very large scenes. So this was kind of important that we kind of preserve this fully convolutional nature. And as you see, the geometry still looks a little bit blobby. We've been working on this and improving this. This was a very recent CVPR paper we had this year. SGNN, I would say, for like geometry completion, that's probably the state of the art at this point. So here we're having on the left-hand side, we're having the partial input geometry, and on the right-hand side, we're seeing the reconstruction. And, I think it's getting more detailed, it's getting better. In this case, we're using a sparse convolution for the generative network. So we're proposing the sparse architecture that only operates where the surface should go. Interestingly enough, the sparse convolution are actually also based on hashes. So it's very similar to the voxel hashing work that I mentioned before, because you need a sparse architecture to run the convolutions only locally where you need them, so you don't waste a lot of the effort in empty space. And the second thing what was cool about this work is it was actually fully self-supervised. So we can train this only on real-world data, and we didn't need synthetic counterparts anymore. So the previous example, you needed we trained this on synthetic scenes and tested in a real scene, so we had this domain gap. But here, these ones are actually trained only on real data, and the idea is kind of simple. It's basically we're having a reconstruction that is relatively complete, and we're taking more frames away, and we're forcing the network to make predictions from a very partial to a less partial scan, and we're masking out everything where we don't know it. And because of that, over the scenes, you can learn a complete reconstruction. So it's not quite perfect, but I think from a geometric standpoint, this is actually already at a pretty decent state, what we can do right now. It's not fixing everything, of course. So, of course, if I'm looking at this, right, again, the geometry here looks relatively good. But we don't have realistic textures. We don't have realistic appearances yet. And we've actually had a lot of papers trying to fix all of these things, right? We had a couple of papers fixing textures. We had a couple of papers trying to get fine scale geometry, like shape from shading we've been trying to do, to get more local surface details. And yeah, it's difficult, right? Like generally in computer vision, we've been working on this for a long time, actually, as a community, probably for the last 30 years, we've trying to get better 3D reconstructions, right? But it is difficult. It is not such an easy task. And even with learning and generative models, it's still not so straightforward. So one of the ideas is now, well, if we can't fix the reconstructions, maybe we should fix the rendering. So traditionally, the rendering here is a standard graphics pipeline, right? We have a 3D model, we have either a rasterizer or a ray tracer, and we're going to create some images out of that. But why can't we change the rendering pipeline, maybe how it works right now? And this is like what gets us to this whole concept of neural rendering right now, where we're saying, well, we have kind of an approximate 3D reconstruction. And from this approximate reconstruction, we want to learn how to reproduce real images again. And one of the work, this is also a work led by Justus Thies here. And what he's doing is he's basically saying, well, let's get a very, very coarse reconstruction. So this geometry here is actually a globe. It's a sphere that is reconstructed with ColMap in this case. It's a multi-view stereo reconstruction. And the idea is now we wanted to learn some appearance information on the surface. We call these neural textures. And with these neural textures, they should kind of encode the local appearance, but they should be learned. They have no like manual encoding. We should just learn how to fix kind of the local detail. And then we have a differentiable renderer that takes this proxy geometry, the neural texture, renders it into 2D. And yeah, then we have a quote unquote a learned renderer. It's a unit that takes these sampled neural textures. It's kind of like deferred shading, but with neural deferred shading. And then it learns how to recreate out of these sampled neural textures an image out of it, again, that should be realistic. And the idea is that this differentiable renderer, as well as 2D unit, they can all be trained end to end. And the idea is then you can basically do novel viewpoint synthesis by just changing the R&T here. So changing the transformation in the rendering should allow us to create new views. And these neural textures are then reprojected into the respective view. And then we have a unit making a real image out of it again. And compared to traditional GANs or conditional GANs that directly operate in image space, this requires significantly less amount of data because we already have hard-coded a lot of the rendering ideas with these transformations. So if you're looking at novel viewpoint synthesis, these are some of the results we're getting. So here's the ground truth. They're of course not part of the train set. And here's the resulting novel viewpoint synthesis that we did with the neural rendering method. And we get actually pretty realistic results here. And it actually looks, I would argue, it looks pretty good, at least for the single object, right? Of course, now the goal is to get this on larger scenes. But it's not only a possibility to novel viewpoint synthesis here, it's also a thing what we can use for scene editing. So here we have another example. This is a bust that we reconstructed again with multi-view stereo here, right? So we have here the input sequence of the RGB images. We get some coarse reconstruction that looks like this. And then what we did is we annotated this bust here. We having the 3D reconstruction of this bust. We have this annotation here that we want to do something to this bust. And we optimize the neural textures for the scene here. And then we copy paste basically this bust here, here, and here, and copy the neural textures, the features that we have on top of it that encode the local appearance. We copy that 2 times here, right? And now the idea is we can do novel viewpoint synthesis with the edited scene. This is something we see here. And we have here the input, the original novel viewpoint synthesis, right? And now we have the edited novel viewpoint synthesis, and we see here we have these statues appearing twice. And I think it looks quite good, right? This is a very simple thing. All you can do right now when you say, well, the reconstruction itself is not perfect, but with the rendering, we can actually produce pretty realistic images. So if you're looking closely, it looks actually pretty good. But one feature we didn't do yet, if you're looking at the shadow, only the middle bust here casts the shadow on the wall. And the reason here is why we don't have it on the other one is because our differentiable renderer is just a forward renderer. It doesn't have any global information. So obviously there's a lot of room for improvement, but I was pretty excited that we actually got it running so well. And this is a thing that you actually can do not only for static scenes, you can also do this for dynamic scenes. And this brings us to one of our favorite applications. I haven't talked too much about it today, but it's mostly for the face editing. So what we can do now is we can basically take a 3D reconstruction of a face that we see here of this video. So we have a face tracker and a face reconstruction method, which is based on the face-to-face work that Justus did before. And the idea here is that now you have the background image fixed, and for the foreground, you take this reconstruction and you want to edit it by editing the 3D model. But if you're just editing the 3D model again, you're not going to get a realistic output rendering because, you know, it's just a reconstruction. It's not perfect. So we thought, yeah, maybe we can also use this neural texture idea. And the idea now is we basically take the 3D reconstruction. We use that to sample the neural textures. So the neural textures are being put into these regions in image space here. And then this on the right-hand side is the synthesized output with our rendering network, right? So it's the same idea of neural rendering. So you have these neural pixels on top of the surface, right? You can, with the proxy reconstruction, you know where to project them. And then you can make realistic images out of it again. And the idea is that we can now take a source actor and can animate the reconstruction, right? So the reconstruction serves as a proxy to drive the edits. Okay, and now we're going to drive the edit, so we just let it run. It should also have some audio in principle. And again, on the right-hand side, this whole thing here is all synthesized.
I would really say moving problem. I would have to say Clinton.
So I think that's pretty exciting. So for things like small objects, for faces, this works actually really well. This whole neural texture work. But of course, there's a big challenge if I'm going back, to my original pitch. So how can we go from 3D point clouds basically, or from coarse reconstructions to something what we see in computer graphics? So often when I'm showing this image, I'm saying, oh, this is what computer vision looks like. This is what computer graphics looks like. And our grand challenge is to make computer vision like computer graphics. So, but instead of having like 100 artists or so fixing it, we want to do it, of course, automatically. This is, I think, a scene from Kitty, where you have a LiDAR scanner, you have a point cloud, but it doesn't look so good yet. So the question is, how can we make it look better? And yeah, this one thing what I wanted to pitch here is we can change the rendering, right? We can do neural rendering, and this is an interesting big challenge, right? Like how much can the rendering do actually? This is an example where we did the neural texture work on this vase here. This is our vase we want to reconstruct and re-render, but instead we're mapping it deliberately on completely wrong geometry. So we're just taking this this cube here, we're mapping the texture on it, and then we have the neural textures being optimized for this wrong geometric shape. But you see the neural rendering actually does a decent job at reproducing the waves, right? It's not completely garbage. It's doing something. But at the same time, it's also not super sharp. Like if you look in here, right, it's very sharp. It's not very sharp here. So if the reconstruction is not good enough, the rendering has to do more. So the AI, in terms of the neural renderer, has to learn more stuff, and it's potentially harder. So the question is still like, how much can the AI do here? So this is like, there's been a lot of exciting work has appeared recently. I'm a big fan also of the very recent neural rendering papers. Like there was this NERF paper from Berkeley. They also use a coarse reconstruction basically with Colmap beforehand, and then they do the radiance field optimization. Again, it also works on objects, but it doesn't work so well on like large scenes yet. So it's an interesting development where this is going. At the same time, we have to think about, can we still make the reconstructions better? So of course, I think stuff like SLAM, post optimization, we got pretty good at as a community. I wouldn't say it's completely solved, but at least for static scenes, we're okay. Dynamics is a whole other thing, like completely like cloth hair, and it's still difficult, but generally speaking, we're getting better at reconstruction tracking, but we're not necessarily like the generative models to produce textured 3D surfaces equivalent to what artists are doing in video games. This is still, it's still a very, very challenging task. I also wanted to refer to one of the state-of-the-art reports that we submitted to Eurographics. There's a lot of people involved, and these are basically the people that do neural rendering. And this gives a pretty good overview, I think, what has happened in the last 1 or 2 years. It's been a very, very active field in neural rendering, and hopefully there's going to be more and more progress. So I hope you kind of see this like line of research where we first do the reconstruction. We have a sparse reconstruction. We're trying to make the reconstruction better, and then we're trying to fix the rendering in order to get more realistic images out of it again, and kind of create this digital replica of the real world. With that, I would also like to come to the conclusion of the talk. I generally think it's pretty cool to have the image synthesis and the analysis together. Like this is something we've been doing in a lot of these works. So we're trying to, do self-supervision by reprojection losses. We're not the only ones, of course. This is a kind of a nice thing when you can do this. And in the end of the day, we're hoping we're kind of solving this photorealistic reconstruction problem. And I think this is a very interesting endeavor. We've made a bit of progress, but there's of course still a lot of work to do. So it's good for us. We still have a purpose, and we know what we're doing every day. With that, I would like to also come to the end of my talk. I would like to thank a lot of people. Once and foremost, my lab in Munich. We're actually growing quite a bit. We have 14 PhD students. Justus is a postdoc with me. He's doing a fantastic job. He probably deserves a lot of credit of this work. And I'm very blessed with having a lot of great students. We have a bunch of visiting professors, and I'm very happy for all the help they give me. I should also say, of course, especially when it comes to awards and things like this is not just my work, right? And to give you a bit of a perspective here, this is my co-author H-index in terms of number of papers. So So for instance, you see I have out of my papers, I have with Michael Oliver and Angela Dye, I have like 23, 22 papers co-authored together. So you can see that these people here, they actually deserve a lot of the credit actually, because they've done most of the work. And I have counted it in total. I have had the fortune of to work with so far 202 co-authors. So yeah, you know, if you want to make impact, you probably want to work with a lot of people. And it's this is one of the things that I really enjoy about academia is, you know, to reach out, and I love to work with new people. This is one of the really good blessings that we can choose to do whatever we want in this regard. I would also like to thank my mentors. I was very fortunate to have, you know, people who helped my career. I hope to do this, of course, with others, but I should mention, of course, when I was in Erlangen, I had my PhD. I was having Mark Stamminger, Günter Greiner. These were my advisors in my PhD. Michael Zollifer was my office mate. I've had the fortunate privilege to be 4-time intern at Microsoft Research. I was working with Charles Loeb and Jerome Izadi. So, you know, when the Connect Fusion stuff came out, and, you know, we worked with voxel hashing on top of it and so on. When I was at Stanford, I had Hans-Peter Seidel was a great supporter. Actually, very funny. I only published a single paper. Last week was the first paper published with Hans-Peter. This was pretty interesting. And then we had, of course, Pat Hanrahan was a great host. Leo Kivas, I've done a lot of stuff. Angela has done a lot of amazing work here. And when I came to Munich, Justus joined me as a postdoc, which was very happy that this happened. And I should mention Rüdiger Westermann, who has guided me through tenure track processes and stuff like this. So he also actually deserves a lot of credit, because he helped me to set up a lab and gave me a lot of good advice in terms of how to structure a lab. Yeah, with that, I'm actually at the end. I think I'm 3 minutes over. I'm not sure if there are questions, but yeah, thanks a lot again for the award. It's really great that we have this community here in Germany, and I think we should definitely work on continuing improving it.
Yes, thank you very much, Matthias. This was a great talk, and I enjoyed it thoroughly, because this is also what in the non-neural times I have been trying to do, but never achieved. So this is really great. And I said also that there is the chat, and you can ask questions to Matthias. Just put it in the chat in the award and talk session. And I have actually one question. When I looked at the work that you did with geometry, and of course we are always picky. So if you have a table, the table gets to be a block. So the occlusion problem, can you say something about this? How good can you handle occlusions? And I mean,
you mean in the reconstruction sense, or
beyond it? So
yeah. So sorry, is the question like how well can we reconstruct occluded objects, or?
Yeah, or how do you handle the occlusions? What can you do? Maybe sometimes you have to hallucinate things which are underneath. What does the completion does?
Yeah, so I mean, if you're just doing straight 3D scanning, right, or if you're taking a video feed, right, we've tried pretty hard to get comprehensive scans of rooms, right? It's fundamentally not possible to avoid occlusions generally. You're always going to have them to some degree, maybe in a larger degree, maybe in a smaller degree, but they're always going to be there. So I feel the only way you can handle that, right, is to just look at various different scenes that have seen objects from various angles and so on, and kind of learn these priors that eventually will hallucinate them. And this is what our like scene completion work and geometry completion work is going to do eventually. If you learn these generative models, right, what they do is they just look at different patterns they have seen in other scenes. So maybe the same chair has been seen from a different angle that was occluded in another scene. And these kind of patterns, and you can show that based on the activations and so on, the network picks up on, right? And this is basically what we are learning. And it's not perfect yet, of course, right? We cannot guarantee that this is specifically that one piece was actually in that scene, but we can make a plausible prediction what is the most likely explanation of that scene. And, you know, given the priors, what we have as humans, for instance, it's almost, we try to make this probabilistic at the beginning to have kind of a partial scene and have multiple explanations. But it turns out, like, we humans are also pretty good at inferring like the missing pieces, and it's a fairly deterministic task. If you're looking at a chair in a room and you see there's like 5 other chairs in the same room with a similar geometry, you know they're pretty much the same chairs, right? And these kind of correlations humans are pretty good at doing. Neural networks starting to get there, but of course not quite there, right? I mean, there's of course a lot of work still to be done, but I think it's actually remarkable that you can get, you know, pretty fine scale geometric detail. It's also remarkable from a processing standpoint how you can run these completion networks to basically sub-centimeter resolution right now.
Okay, yeah. One more question about the dynamics. So if you have really deformable scenes, you showed that there is the neural texture can handle some of these. How far can you go?
That is a very good question, because that is one of the most challenging things. So static scenes, it's getting better, right? But dynamic scenes is harder. So the neural textures, this works really well for faces because we have a really good face reconstruction. So the tracking of the face, we know basically a 3D model in every frame where every point goes and so on. And this allows us to train the neural textures pretty well because, you know, we know this one neural pixel or this one surface point has to have a certain appearance in every frame. And if this mapping would be inconsistent, this wouldn't work so well. So in order to get this for, you know, more generic objects, let's say you have clothing, neural rendering on clothing is a pretty hard topic, of course. I want to capture a human, and that is a very challenging thing. But the reconstructions for humans is pretty difficult. So I mean, there's domain-specific method like Michael Black's lab in Tübingen at the MPI. They're doing a lot of fantastic work in this regard. But it's not at the same level yet what you have for faces. So faces is more accurate. That's why the neural rendering works specifically for the faces. But then when it comes to, you know, clothed humans, I mean, Gerard Ponsmall, he's at the MPI in Saarbrücken right now. He's doing a lot of stuff on cloth right now. It's getting there in terms of the reconstruction, but the tracking is still not quite there what you would need in order to, you know, like do neural rendering to a perfect level. So I think what's going to happen is we have to do this as a joint problem, right? We have to jointly solve reconstruction with re-rendering, and kind of when once you do that, you can jointly optimize for appearance and jointly optimize for the non-rigid pose. And I think that's, I mean, we are working on this right now in the context of non-rigid reconstruction. But of course, there's going to be a lot of work coming up because I think this is a very fundamental challenge to have these dynamic objects part of the neural rendering methods and so on. And, you know, this is probably where we're going to go as a community too.
Okay. Simone Frintrup asked a related question. Great talk, thanks. Can you say something about the ethical implications of the neural texture work and how to avoid misuse?
Yeah, this is actually a very important thing. And I mean, I didn't have too much time today to go into it. But one of the things we have to realize generally in this work, right? I mean, the whole point, what we're trying to do is we're trying to create digital duplicates of the real world, right? And that means, of course, that we can create any kind of video. We can create any kind of image. We can make people possibly even say certain things that they, you know, wouldn't do in real life. And the ability to do photorealistic video synthesis, specifically of faces, has, of course, you know, sparked a lot of ethical discussions. Like, is that something we should do or not? So on the one hand side, it's actually not a new thing. People in movies have been doing this for a very long time. Like if you're looking at blockbuster movie, a lot of the stuff is actually computer graphics. Also, the faces are digitally altered when you have like a stunt double or somebody like that, right? They're not actually part of the movie, and the face is being replaced. So it's kind of a fake. Well, movie by definition is fake imagery. But of course, what we're doing right now is making the whole process a lot easier, right? Just like having a half $500 million budget to have a blockbuster movie, we're having a webcam to record you, and then you can change the facial animation, right? So the level of complexity goes a lot down. And we are very well aware of the potential misuse. And specifically for that, we're actually working on also trying to figure out, can we still detect that? So we have one big effort, which we call face forensics. This is led by a PhD student, Andreas Rössler of mine. The idea is basically, can we automatically and reliably say, is this a video that has been generated by one of these AI methods? And this is currently in the academic community, I would say it's the largest effort in this regard for faces. It's specifically targeting deepfakes and facial reenactment methods. And interestingly enough, the detection, when you know the method, is much easier than generation of fakes. Because you only have to figure out, oh, 1 pixel was off, right? And if I know that, it's kind of a fake imagery. So yeah, that is a pretty interesting direction where this is going, especially when you go into methods that you haven't seen before. So when you have new methods, generalizability, this few-shot learning in terms of, oh, is that a new method we already know, and so on. But yeah, on a high level, we're working a lot on the forensic side there too. We actually work with fact checkers, nonprofit organizations together, and trying to explain on one hand what is technically feasible, and on the other hand, we also we're trying to make sure that there's also methods to possibly detect what we're creating. But I think as an academic, right, we have of course the responsibility to first of all be educational, right? We have to explain what can be done. How easy is it really to do that? And then second, we also have to provide methods to kind of deal with that content we're doing. So I think looking at the ethics is extremely important. We have to be very careful how to do that. And again, we also have advised our federal government on this. But I think at the same time, we also need to see the possibilities. I mean, the one thing I'm currently still sad in a sense is we're having all of these meetings via Zoom, we're having this talk via Zoom, and we're far away from having an immersive, like remote collaborative workplace, right? Why don't we have that? And eventually this will lead to, we need to get more reconstructions of people, we need to get 3D models, possibly some combination of null rendering. And we need to think about how we transform our work environments and go on beyond like a Skype call or a Zoom call to something that is, you know, a little bit more interesting, right?
Okay, thank you very much. I guess that is a good finishing also. I would like to thank again all the awardees that received the awards, and this concludes this session, and we'll have a break for lunch. So Matthias, thanks again and goodbye.
Thank you. Bye-bye.